Hi everyone and welcome to this new class in which we will be discussing high lift devices in aerodynamics. So, first of all, why would we need some kind of high lift devices? Right, so as we mentioned in previous classes, what we usually have is that the lift is more or less similar than the weight. It has to be equal to the weight at cruise. But in general terms, we can just assume that it will be very close, the lift and the weight will be very close one to each other. So by this definition, the weight of the aircraft will basically be very similar at the beginning of the flight, and throughout the flight. It may be a bit different from if we compare the initial conditions to the final conditions of the airplane, since we will have some fuel that we used, but in general terms we can assume, at least for some calculations, for some instantaneous calculations, that the weight is actually constant. So by this definition, the lift can be assumed to be constant at one point, right? So coming back to the equation of the lift and assuming that the lift is more or less equal to the weight and the weight is actually constant, we see that all of this has to be a constant, right? So if all of these parameters have to meet a constant, then this means that if the velocity changes, which will happen when we are accelerating on the runway, when the velocity changes, and assuming the density is constant and the surface is constant, it must mean that the coefficient of lift has to change in order to provide more or less weight. And since the weight is constant, as I mentioned, if the velocity is small, we need a high coefficient of lift. And if the velocity is high, we need a small coefficient of lift. So these two variables will change one with respect to the other. Right, so imagine this. Imagine that we have our aircraft and we want actually to take off this aircraft, right? So why would we need high lift devices? So the idea is that at low velocities, which is the case at takeoff, when we're taking off, we need relatively low velocities in order to take off, it must mean the coefficient of lift is actually very high. So high lift devices, what we'll do is actually increase the coefficient of lift. Right? This is what you need to know. We will have an increased coefficient of lift so that we can actually lift off, and take off at relatively small velocities. And why is that? Well, if we had very long runways, we would have a long distance in order to accelerate our aircraft. However, just by using a higher coefficient of lift, it means that we can actually lift our aircraft, at a certainly a bit smaller velocity, and that's the idea. And if we actually can take off at a bit lower velocity, it means that we need smaller runways. This is just the idea. So my answer would be this: why do we need high lift devices? In order to have smaller runways, right? Because this would imply a higher coefficient of lift and therefore a lower velocity. And starting at a given point, we will actually be taking off at a smaller distance if our requirement is at a lower velocity. I hope that's clear. As we mentioned, the coefficient of lift will depend on the angle of attack also, right? But we can't just increase a lot the angle of attack. What we need to do is actually to provide additional lift devices. Now, in this graph, we see how different elements, high lift devices will actually change the coefficient of lift with respect to the angle of attack. Now, first of all, we will be discussing flaps, I'll talk in detail what flaps are in a bit, but for now, I just want you to recognize the different elements, So this would be the normal curve, just a generic curve of a coefficient of lift with no additional high lift devices. This would be the curve if we introduce a flap, okay, so if we actually put some kind of element on the trailing edge of our wing in order to increase the lift, okay, you can see that basically what we're moving is the curve to the left, right, or upper. You can see it both ways. I prefer to see it as moving it into left, because this means that if we are at this angle of attack, okay, instead of providing this lift, we will be providing actually this lift. So you can see that the lift coefficient is actually higher, right? So this is the effect with flaps. Flaps will actually move the coefficient of lift curve, right? And if we introduce also slats, okay, like in this black line over here, what will happen is that we actually are able to prevent the curve, this curve of the coefficient of lift to stall. Okay, so instead of just decreasing, we will actually be able to maintain the increase, the linear increase, okay, at higher angles of attack. So the idea for slats is that you can continue at higher angles of attack and still be able to provide lift without stalling, okay, without having the decrease of the coefficient of lift, which happens at high angles of attack. Now, let's discuss this a bit in more detail. Flaps, what they do is basically you have an additional surface, okay, which can be moved from this point over here, okay, to the back. There's different kind of configurations also. You have plain flaps, which would be just by definition a constant flap, okay, it's not very optimal. Split flaps, which is just some element moving like this, and Fowler flaps, which are the most common, okay, which is some kind of, you can see this kind of little wing, okay, you would say. It's just kind of a surface which moves from this point, okay, like in this case, from this point to the back, right? So what happens with flaps is simply that. There's some kind of downwash because we have the extension of this part of the wing, okay? So even at zero angle of attack, right, or something like zero angle of attack, the air will come and still go down, right? So there will be a change in the direction of the air even at angle zero of angle of attack. So this is what I meant before by changing the angle of attack, by changing the position, okay, the location of the curve of the coefficient of lift. It's simply really chat. The basic idea, the basic physics is simply that. We have an extra downwash, and this extra downwash is related to moving the coefficient of lift curve. Okay, so for instance, at zero angle of attack, for this airfoil, we will have this coefficient of lift, okay? And for this same angle of attack, if we add this part of here, which would be the flap, we actually get a higher coefficient of lift. So this is what you need to know, right? This is what flaps do. So it is basically equivalent to increasing the angle of attack. So yeah, that's what you need to know. This would be the flaps. Another interesting phenomena is with all the discussion that we need to do also of laminar versus turbulent flow, okay, which we will do in the following class. Right now, what I need you to know is that there's some kind of device, the slats, okay, is designed in order for it to be located on the front of the airfoil, okay, on the front of the wing. In this way, what we'll be able to do is to transfer some of the wind, okay, which is over here, which otherwise would go down, or otherwise it would kind of behave unstably over this point, okay, over this surface, over this part of the wing. And what we do is direct this air into the slot, okay, which is the slot that we have between the slat, which is the physical material, and the wing, okay. So by providing, it may be, it may seem a bit stupid, but the idea is quite clear and it works very effectively. What we're actually doing is transferring some of the wind into the top of the wing. Okay, and because we're doing this, we are helping a lot the conditions of laminar flow on top of the wing, right? So basically what we are doing is avoiding the turbulent part of the flow, right? So how's that transferred to the coefficient of lift curve? Because basically, instead of getting this decrease due to turbulence, okay, what we will have is that actually we can continue to provide linear increase of the coefficient of lift at high angles of attack. So by including the slats, we actually are able to increase more the angle of attack. And because we can increase more the angle of attack, we will be able to get more coefficient of lift. Okay? So we get more lift just by providing a laminar flow on top of the wing. This is what you need to know for slats. Just checking. Yeah, so it is important to relate, okay, that the turbulent flow is what actually causes this decrease in the coefficient of lift at high angles of attack. As I mentioned, we will discuss this in better detail in just the following class. But right now is what you need to know. Slats operate in order to avoid the turbulent flow from appearing. Okay? So some of the flaps that you can find in commercial aircraft would be, I'm sure you've seen this many times, like this ones. Okay, this photo is quite interesting because you see the flaps, right, on this part over here, all of this surface, and you can actually see that there's kind of a hole, a physical hole, okay, between the wing and the flap, which is what we saw over here, okay, that it can appear a hole, okay, on this part over here, and that's not a problem at all. The flow is continuously downwashed, okay. And you can also note in this photo, there's a couple of more elements. You can see the spoilers, right, used on top, which they basically spoil, okay, very literally, they spoil the flow. So you have a specific flow going over here, and if you just put the spoilers in the middle, the flow will actually get spoiled, or basically you will have a lot more drag. This can be used in order to slow down the aircraft on when landing, for instance, or in general when you are interested in slowing down the aircraft at any point. Okay, so this would be the spoilers. These are the flaps, and also you have the guide flap tracks, okay, which are quite interesting, which is the main track where the flaps move. Okay, so you can see that the flaps are actually moving on top of the guide flap tracks, which are this pointy part, okay, over here. I'm sure you probably have noticed it also on aircraft. The idea is that the flap actually moves on top, okay, of these guiding flap tracks. Right. This is the view of a 747. You can see the guiding flap tracks, as we mentioned, and also the different level, the different slit, okay, of the flaps on this part over here. I just like the 747 because it has a very distinctive flaps, and you can also see the slats over here, okay. So yeah, so this would be flaps. I'm sure you already know what flaps look like. And slats are basically this part over here, okay. So as we mentioned, they are on the leading edge of the wing, and they just provide a path for the wind, okay, to go from the bottom to the top of the wing, okay, in order to increase the laminar flow on top of the wing and to avoid the detachment of the flow, okay, of the appearing of a turbulent flow. Right, so here you can see, for instance, the difference between the slats when they are operating in this part over here and when they are closed. Okay, so this is the slat configuration, and how we discussed already how it will affect, okay, the laminar flow on top of the wing. So this is all. We can move to the next class.